Alright, I'm going to go over Chapter 5, Number 7, which reads, a ball on the end of a string is revolved at a uniform rate in a vertical circle of 72 centimeters, as shown in the figure right here. Okay. If its speed is 4 meters per second and its mass is 0.3 kilograms, calculate the tension in the string when a ball is A at the top of the path and B at the bottom of the path. Now, one thing that I want to mention is the book is nice enough to actually draw free body diagrams for you here, okay? When it's at the top of the path, since this is a vertical circle, you have gravity and the tension of the string both pulling down. But where at the bottom of the string, you got m of g still down, because gravity only acts in the one direction, towards the center of the planet, but the tension force is now acting towards the center of the circle. Okay, so you'll see that the unbalanced forces are going to be a little different. At the top, it's the combination of the gravitational and the tension. But at the bottom, it's the difference between the tension and the gravitational. Okay, so the picture in this case does tell 1,000 words there, okay? We could go on and on and on and talk about how these forces are different. Maybe not 1,000 words, but you get the point, okay? So let's go ahead and try to solve this problem. Okay. So the first thing that I'm supposed to find, I'm supposed to calculate the tension in both of them, okay? So in order to calculate the tension, since it's going to be a difference in two forces, I need to know what the unbalanced force is, okay? Now, again, in circular motion, the unbalanced force is the centripetal force. So the first thing I'm going to do is I'm going to solve for f of c, which is mv squared over r. And they said that the mass was 0.3 kilograms. It was moving at a velocity of 4. Don't forget the squared. People oftentimes forget the square. And then it was a 72 centimeter circle, so we got to change that into meters, 0.72. And if we do the math here, should get 6.67 newtons. Okay. Now, I want to take a look at this at the top. Okay. Remember that at the top of the circle, both mg and the tension force were acting in the same direction. So I could say that the sum of the forces, which is the centripetal force, would be equal to mg plus the tension at the top. We'll call it tension 1. That's what it was called in the picture. Okay, and then at the bottom, I could say that the sum of the forces, which again was the centripetal force, okay, would be equal to the tension, Ft2, minus mg. So now that I solved this, I have something here, and I knew the mass, okay, so I'll be able to solve for this. So if the centripetal force here is 6.67, mg was 0.3 times 9.8 plus ft1, and in this case we'd have 6.67 ft2 minus 0.3 times 9.8. And again, if we go through and we do the math, ft1 here gets 3.73 newtons, and for this one, ft2, we get 9.61 newtons. Now, let's think about this logically. Does it make sense that the tension force is less at the top? Well, sure, because gravity is helping us bring it back down. And here, does it make sense that tension is greater than that? Well, yeah, because it's got to work harder. It's got to work against gravity. Therefore, the tension goes up at the bottom. Okay? All right. Hope that was helpful.